Good afternoon. Well, welcome to everybody who decided to join us for SanoSeminar. Let's wait maybe 3 minutes to give chance all other potential participants to join us. Well, this seminar is after quite a long break, which one of the results of this break was Krakow Conference on Computational Medicine, which was a time for related also a time for preparation for participation in this conference. So for this reason, many people were busy, and September was a time when colleagues from Sano were traveling to many conferences. So we decided to restart just now. And well, from this year, we will have 3 seminars in each week, in each month. The last seminar time will be devoted for internal meetings of Sano team. So there are more and more issues which should be discussed, and it seems that only Sano is the best, Sano seminar is the best time. But anyhow, well, we have, I think, quite a large number of participants at that moment. So once again, welcome everybody. And today we will have as a speaker, we will have Jan Meizner. Jan, at that moment, well, is recently employed in Sano as a PhD student, and Jan is working on the area which he knows pretty well, namely he is elaborating solutions which enable many people to use computer resources available in Krakow, especially in such a way that they are used in optimal way, thus well, eliminating all these losses which are related with non-used processors on parallel computing and so on. And well, when we have a lot of large amount of data in simulations related to computational medicine. So today the topic will be also related with somehow managing access to memory. If you, as usual, we will have a discussion after the seminar, but if you have a question which is important from the point of view of understanding the talk, please interrupt and write the question. I will try to transfer this to Jan. So Jan, floor is yours.
Okay, thank you very much. So yes, my PhD work focuses on all kind of performance modeling prediction and generally facilitation of running medical applications on modern infrastructures, including HPC and clouds. But in this talk, I would like to focus on memory-intensive applications. Why? Because first of all, if we have insufficient compute power, we may need to wait a bit more, but in many cases we can solve the issue. If we have insufficient memory, then, well, our job will just run out of it and crash. So it's not what we want to have. And while high performance computers, as name suggests, have both high performance and are large in all kind of resources, they're not always sufficiently large for every, let's say, use case. Especially we have some interesting bioinformatics and genomics in special use cases that require huge amount of RAM. By huge, I mean sometimes even over 1 terabyte of RAM per node. Certainly, we have such instances in the cloud, but well, many HPC clusters came from a high energy physics background and other simulations background that were more CPU bound and memory bound, and in turn, while providing huge computational resources, their memory resources are a bit more limited. And also, there is an important class of application that needs to be run on many nodes, but requires some shared portion of data. So loading this data on each time, not just each time, but on every node is wasteful, and it's also something we want to address. And let's start with some related work. So I mentioned pipeline. This is of course one of the samples, but we wanted to focus on something. So, well, the interesting part here is Starliner, who that needs to load a portion of data called indexed into memory, and we've done some testing how this index behaves, and found out that, well, there is an interesting pattern. So basically, some portion of the index is accessed much more frequently than other. So, and in turn, it would be, well, it seemed beneficial for us to find a way to well, share it. So there is a different view of the same aspect, and finally I think this one shows it the best. So we found out that, well, caching around 20% of index would give us around 80% of hits. So it would be prudent to find a suitable solution for that. And well, now coming more into the solution. So what we want to achieve. So basically, we are planning to somehow share, or we planned to share data in between the nodes. By itself, the issue has been solved many times, but our important constraint for us was that we wanted to do it on, let's say, on a multi-tenant existing HPC cluster without involving system administrators and without requiring to have any low-level access, like especially we don't have root level access on those clusters. Certainly, we could have gone to the system administrator, ask them for assistance in deploying the solution, but it wouldn't be, well, prudent to do it for forever, and it wouldn't be even possible to do it for all cluster in Europe or even outside. So we were looking for a solution that would, well, with minimum latency, solve it for largest quantity of applications. What's also was important for us was to be able to address both open source applications and closed source applications, as many simulations frameworks are, well, are closed source, which means that we cannot actually change the application itself. We need to have a transparent solution for that. So just getting back for two biggest issues we wanted to solve. So one on the bottom is the case, actually one on the left is the case I've mentioned. So the one where we are, when jobs running on multiple nodes tend to share a portion of memory, so we can free up some memory if we are able to split this block and access from multiple nodes at the same time. On the right side, we have a different case. So, I've already mentioned that sometimes it can take up to or over 1 terabyte of memory per node so combined memory of multiple nodes would solve that, but by default, of course, we have access just to this single node, and hence the need for the solution for that. And what I can what we started, we already, well, maybe mention those. Already mentioned that. Okay, so I've already mentioned that there are existing solutions, and here are those examples. Like RMAP is a solution that based on custom-made kernel module. There is also an operating system called Lego OS, which is purely designed as a distribution for this kind of processing. But certainly we neither can replace existing OSs on big infrastructures, nor we can load modules or modify kernel without the involvement of the owners of the cluster, which is what we want to, well, somehow not to do for obvious reasons. So what I wanted to do by designing the solution was to look what's available for the regular user. So obviously there is the well-known standard called MPI, message passing interface, that used to run computations on the cluster, but also it provides for many years one so-called one-way communication that can be used for moving data between nodes running an MPI job. And there is well, shared file system commonly used on like last in case of our or let's say in case of Cipernet's and PL grid in general clusters. So this prompted those two solutions plus one showed as a baseline. So basically, one of these solutions utilize shared storage and mapping files into memory and the second one involves using, well, aforementioned one-way MPI communication functions. So first, why two solutions? Obviously, there is not usually one solution don't fit all cases. So we expected that the solution based on MPI would be far superior in performance. However, the direct way that we tested in the beginning required modification of applications, as we were by replacing regular memory access with those functions. This can be we can do it for open source applications. Sometimes it might be easier, sometimes more complex, depend on the complexity of the application itself, but it can be done. It won't. We cannot do it for application that to which we do not have, well, in cases we do not have access to the source code. So to address also this case, we combine a set of solutions like mapping, well, creating a library that can be preloaded with all the preload mechanism, and that replace regular memory access functions by our own, which are based on, well, a virtual file system stored on kind of shared file system. Obviously, we expected it to have far lower performance, but it was a kind of proof of concept to test our theory. And to check the results, we've run some tests on 2 supercomputers, so RS and Helios. Helios is currently the fastest supercomputer in Poland. RS is the older but still very powerful machine. Both are at Cyphernet. And we measured a set of data transfers and collected the results as there and presented them here in those 2 diagrams. So as expected, the virtual file system based solution is definitely slower than baseline, which is the red one showing simply local memory access. But on the other hand, if we use MPI, we are getting really similar results to local memory access. Obviously, network and other, well, network must introduce some overheads, but they are well within what we can call the tolerance level. So what we wanted to do is to devise a new solution that could somehow merge those 2 into, well, benefits of both solutions into one that we can use. So we started with, well, the idea to create the dedicated file system based on, well, file system in user space mechanism that can be run without the need to have low-level access or high privilege access, and which would use MPI functions as a backing mechanism. And we've already started development of this solution, and we hope that it would provide, well, let's call it best of both worlds. So it would allow running unmodified software, so in turn allow to run, let's say, also proprietary solvers, but would not require well, any modification of the OS, and would support and would not have issues that, well, are inherently related to using some intermediate file systems, which is already obviously far inferior in performance to random access memory. We also would be able to get the benefits of features of MPI, such as such as direct memory access to reduce overheads related to processing of data in CPU. So, well, I would like to start drawing some conclusions. So we've managed to build a solution based on those two, based on those two notions. So virtual file system and MPI. And we've run benchmarks on those in those two cases. As expected, use of files, especially shared file system, introduced significant bottlenecks and impacted performance significantly. But we still believed that it can be used for some lighter cases, as the overhead is around 10 times the baseline value. So if there are cases that cannot be addressed the other way because they cannot be modified, but and cannot run on single node due to lack of sufficient memory resources, we still would be able to run it just, let's say, 10 times slower, but might be sufficient for jobs running, let's say, in minutes. On the other hand, we found out that the MPI-based solution provides comparable performance to local memory, which was really which is really optimistic for our future solutions. And as I mentioned, we started working on the solution, merging those two notions into one, and on which I am now working. So I hope to achieve. Oh, sorry. So that's slight interruption. So yes, my current work mostly focus on development and testing of file system fuse-based solution. Also, I've done some research on other options and found out that Open Fabric interface, or also known as libfabric, might be a good solution for, as an alternative that would not require involving MPI and that still would support many interconnects, because our goal is to support as wide range of interconnects as possible. Even at CipherNet we have two distinct interconnects. So the older cluster uses InfiniBand, the newer uses Slingshot as it is a Cray cluster. So obviously we are looking for, we don't want to re-implement, if possible, the solution for every common interconnect. So that usage of libfabric seems prudent from our point of view. What's more, I've already spoken with some people from our functional genomics team about possibility to widen the pool of use cases, as we are always looking for interesting use cases to advance our research. And while genomics use cases tend to require a lot of memory, there are certainly other applications from medical domain that have similar requirements, and we are always looking for those applications and those use cases. What's more, it may be your application. So if you have some interesting medical applications that require, well, let's say huge amounts of memory, or just more memory than it's available in infrastructures you usually work with, or maybe you have case similar to the first one I mentioned, so the one where you are running multiple jobs on multiple nodes, but each job shares a portion or maybe the whole data. Then we would like to hear from you about your application, and if possible, we would try to help in optimizing it well, and make it either enable it to run smoothly or run at all. So, well, with this, I think I'll conclude my presentation, and I'm open for any questions, suggestions, and comments from your side. So thank you very much. And
thank you very much. Well, now we have time for questions for discussion. Could you please come back for a while to slide, I think, number 14?
The one?
Yes. Well, because there are some results about, as I understand, time to access to local memory. Would it be possible to make it a bit larger? Because I would like to understand what is on them.
One moment. I'll try to. I will go out of. Yes. So actually, there are two cases. One mirrors the other, because one is on Helios, one is on Ares. I will try to make it even bigger. Okay.
It's a bit better. So they are very similar. Yes. So it's.
Yes, those two are actually quite similar, but well, the biggest difference is between this green line and those two. Okay, so the base case is the red one. So the red line is about, well, also local memory. Also, what there is MEMS PI. Maybe I need to say why. So here I presented the most common case, but we tested the solution using two notions. One which we could call naive, so the copying byte by byte, and obviously it was way less performant, and another one using block memory copy, so with MEMS PI. And the baseline, well, actually on the previous on the previous slide are those three cases. So local memory is just as a reference. This is one used last, and the third uses MPI, and this is reflected here like the red one is the first one, so it's just for comparison. The green one is the second, so the middle on this diagram, and the third one is the right one. And well, what is the most important for us are those two lines, so red and blue, because we want, well, we hoped them to be as close as possible to each other, and what more, and the green one is yes, one based on the usage of the storage as well, reverse of RAM disk. Yes, so it's not like we can have we usually are not. It's more like probably close technology would be to swapping or to virtual memories. But we've done it just to test the solution. And what I can more say, of course, this is the time, and this is the size of the data chunk.
Well, another question which I would like to ask, you have in your summary of your results, you said you have presented that if that solutions which are based on memory access with MPI are quite successful. Yes, this is MPI-based solution provides comparable performance with non-distributed memory access.
Yes.
So is it the result that this version of MPI was somehow tuned to the architecture, or it is
not yet? And actually, if I can say, one of the issues we've got is that one of the MPIs, this on RS actually was performing better than one on Helios. Maybe not better performance wise, but better. Well, we had to use two different MPIs because on Cray only Cray MPI worked properly and not open MPI, but it handled a bit different. Well, we were able to move bigger chunks even than showed here on RS. We were unsuccessful with Helios. So maybe some tuning or well discussion with administrators would certainly help in that. Or as well backup solution, I've tried to check how to use let's say other solutions like the mentioned libfabric, so directly accessing interconnect instead of well using MPI. Obviously, MPI is very well optimized, but it's by itself. So I've done also a test of well some generated code interacting directly with libverbs and with InfiniBand, and this code has lower performance than MPI solutions. So it seems interesting because, well, obviously it should have been less, let's say, there were less layers, yes, because MPI in turn also spoke with the same library underneath, but it certainly, well, MPI is here for many years and it was and it has been tuned and optimized so in a way that it still provided better performance than lower level solution. So yeah, but it certainly also gives room for improvement. So obviously we can try to develop solution that wouldn't maybe not be better, not better than MPI, but we are using MPI. Well, we are just using a small subset of MPI functionality for our tasks. So maybe better for the job. Let's put it that way, because well, MPI is well-established standard, and for regular operations like running computations, it certainly is not going anywhere, in my opinion.
Well, I understand. And well, but the question of MPI is not MPI itself, but I think how it is optimized for a specific architecture. So it's
yes, and this is interesting. Also, we want to go a bit further with this research, because I need to tell that for now we used just one partition of Helios, so we used the regular CPU partition to be well comparable with RS, as RS is well mostly is a CPU cluster with some GPUs, and So for Helios, we use the partition with AMD processors, so regular x86 processors, yes. But most of Helios are grasshoppers and GH200s, and this also might be an interesting case, especially that they already utilize a unified memory between well, CPU and GPU, we can call that, yes, because grasshoppers are ARM CPUs with with NVIDIA GPU cores with sharing common memory. So that would be probably also this is something we will be looking for to test to run jobs on multiple nodes. But yes, we are trying to do it step by step, and for now.
Yes, I understand. So the last item of this future work is help to optimize applications. I understand that it could be something which will help to optimize users' application, but probably it will be necessary to, if somebody is thinking about this type of application, it will be necessary to change something in the code, yes?
Maybe not, but first of all, it transcends this seminar. So obviously, as I mentioned in the beginning, well, just optimizing memory-bound applications is just one of my part of my PhD related work. So if there are applications that require other kinds of optimizations, we are also open for that. And sometimes it may require modification of applications, but sometimes it may just well be a question of fine-tuning or using different kind of maybe libraries or different architecture or way to deploy the application to find some bottlenecks or there also it can be that the application is underutilizing the infrastructures or using too large infrastructure. So in my previous work, I, for example, found out that there are applications that are not well parallelized, but are being run on huge nodes. So say out of 48 CPUs, we are utilizing one core, one CPU, in which case we can either try to parallelize the application or deploy it in a way that it would utilize the infrastructure better, or scale down the infrastructure if it's not needed to, well, if for example, computations are fast enough, we don't want to allocate resources which are not needed, and it's all especially crucial, for example, for cloud systems where we are paying for resources and we may be paying for big instances where, well, much cheaper instances would suffice, but we need to, well, know we can't bluntly cut every instance because it would hugely impact the performance if the instance is actually properly utilized. But in some cases, yes, we can either make it faster or make it less expensive in case of, well, and even in case of obviously in case of HPC systems, even if they are free to use by the end user, they are still being paid by some institutions or some funds. So we need to take care of not, well, underutilizing them whenever possible.
Okay, so many thanks. I'm looking for other people willing to ask questions. And to be honest, there were something like 24 participants, and I do not see any any more questions. So
I will maybe go to the last slide. Yes, there is my email. So if anyone have either questions or want to discuss possible collaboration with regarding their applications, I am, as I said, more than willing to oblige and help wherever possible.
well, I think that this is a good conclusion of your talk. Many thanks. So we will meet at SanoSeminar in 2 weeks from now. In 2 weeks from now, because on next Monday there is not only in Sano but in many institutions in Poland there is a holiday, and so for this reason there will be no Sano seminar. On November 10, we will have the Sano seminar on Monday, on November 17, and it will be something different. It will be about ultrasounds in medicine. So many thanks for being here. Thank you, and see you in 2 weeks from now. Goodbye.
Bye.